Okay. All right. Good afternoon, everybody, and welcome to the PetroTeach webinar. My name is Hassan Karimai, represent PetroTeach today and act as facilitator in this webinar. So, PetroTeach is a global provider of high-quality training solutions to the oil and gas industry. Currently, we are providing about 200 training courses by up to 60 distinguished lecturers with high track record from both academia and industry. Our training styles include online, public, and in-house courses. Due to the COVID-19 pandemic, PetroTeach was more focused on the distance learning during last 2 years. However, we are happy to inform that we have established again our face-to-face courses in different locations for the year 2022, while keeping virtual-led instructor possibility option for our clients. For more information, please visit our website and download the course catalog. You may also follow us in social media such as LinkedIn, and do not forget to watch our videos on the PetroTeach YouTube channel. So today we will receive latest updates on the underground CO2 storage and important consideration on this subject by Dr. Babak Moradi. Materials to be covered in the ongoing webinar and will be used in the upcoming course is related to the Babak valuable experience and comprehensive research on this topic. Yes. So Babak has more than 17 years experience in oil and gas industry. He works as ex-Baker Hughes as project manager and senior RE, senior reservoir engineer. He has background in multiple disciplines: enhanced oil recovery, reservoir management, surveillance, field development, reservoir estimation, and carbon hydrogen storage. Babak worked on several CCS projects, including simulation modeling and CO2 storage evaluation studies. And Babak is based in UK. Babak has involvement in SPE, EAGE, and IPS, and he's a regular presenter, course instructor, media releases across multiple topics and disciplines. So Babak got his PhD in 2016, master from IFP France in 2005, and bachelor in 2003, all in petroleum engineering. So let's move to the presentation. I want to remind you all that you can post your questions, and at the Q&A session after the lecture, some of them will be answered. So please mute yourself, and I'm going to hand over the talk to Babak to address his presentation. Here you are, Babak. Please go ahead.
Thank you very much, Dr. Hassan. Good morning, good afternoon, and good evening, ladies and gentlemen, dear friends. As I think that we have participants from all over the world in this webinar. So, as Dr. Hassan mentioned, today I'm going to talk about CCS, or underground carbon storage. First of all, we will have an introduction to energy transition. We will talk about an introduction about CCS, or underground carbon storage. We will have a talk briefly about geological CO2 storage. After that, we will go to how to estimate the storage capacity of any CCS projects, and we will have a brief introduction to dynamic simulation of any CCS projects. And the main aim of this webinar is an introduction to our main course, which will be scheduled for next month. So I'm turning off my video that you can concentrate on the contents of this webinar. So, as you are aware, the atmospheric CO2 concentration has been rising sharply. In year 7050, the CO2 concentration was about 277 ppm. But in 2023, that has been increased to 419, up to 51%. So we have a huge increase in the amount of CO2 concentration in atmosphere. As you can see from this figure as well, in 1960, the CO2 concentration was about 316, but in 2023, that's reached to 419. This figure shows us the global fossil CO2 emissions. And as you can see, in 2022, the amount of CO2 emissions from fossils was about 37.1 plus minus 2 gigatons of CO2 in year 2022, which is again 63% over year 1990. In year 2023, again, it has increased to 37.5 plus minus 2 gigatons of CO2, which means that about 1.1% increase in the amount of CO2 emissions from fossil. This global maps shows us the annual CO2 emissions in 2021. These emissions coming from fossil fuels and also from industry. And as you can see, China is the largest or biggest emitter. After that, we have United States, India, Russia, and some oil producers, as you can see from these maps, are the higher and highest emitter of CO2 in the world. So by this introduction into CO2 emissions and CO2 concentration in atmosphere, now we are going to talk about energy transition. What is energy transition? Energy transition is a pathway toward transformation of global energy sector from fossil-based to zero carbon by second half of this century, by 2050. So what is the aim of energy transition? The aim is to reduce energy-related CO2 emissions and limit the climate change. How we can do that? By decarbonization of the energy sector, which is urgent and require urgent action. And while it's needed, we need to reduce carbon emissions and mitigate the effect of that on our climate change. Currently, renewable energies and energy efficiencies can achieve to 90% reduction in our carbon. What are the key evidence of climate change? We know that from the media that our climate is changing currently. So what are the evidence for that? We know that the climate is warmed. It means that the temperature is increased. So we have many independent indicators from high up in the atmosphere and to the depths of the ocean. That includes, first one, increasing the surface, atmospheric, and ocean temperature. The second evidence is shrinking of glaciers. CO2 emissions have raised temperatures even higher in the poles. And as a result, glaciers are rapidly melting, calving off into the sea. So we can see the shrinking of glaciers currently. The third evidence could be decreasing the snow cover and sea ice. Decreasing the snow and ice cover decrease the reflection of the sunlight from the Earth's surface. This increases the amount of light absorbed by the water and land, which increase regional temperature. And the fourth one is rising sea level and increasing atmospheric water vapor. Extra water vapor in atmosphere falls again and extra rain, which can cause flooding, which currently we can see in several countries that we have or had heavy rains. So what is net zero and what is the aim of net zero by 2050? Achieving net zero emissions means our economy either need emit no greenhouse gas emission or offset its emission. How we can offset it? By planting, for example, trees, or by technologies such as CCS or carbon storage, which in this webinar, we are going to talk about that. In the UK has joined 120 countries in committing to be net zero emissions by 2050, including all our G7 nations, Canada, US, Germany, Italy, France, and Japan. So by this introduction into energy transition and net zero, let's see what is CCS and what does carbon capture and storage mean. So the definition is that CCS means carbon dioxide capture and storage, or CO2 capture and storage. We also have CCUS, means that carbon dioxide capture, use or usage, and storage. What is the aim of CCS? That's one of the way to mitigate and one technology that we can mitigate our climate change. And the main goal is reduction of CO2 emissions to atmosphere. The principle of that is that we are capturing the CO2 from atmosphere, from waste water streams at emission source, and then we transport it to the storage site, and then we inject it for a long-term isolation from the atmosphere into a deep subsurface. So this is the definition and principle of any CCS project. So again, in this picture, as you can see, we can capture about at least 90% of emission from fixed emitters, from clusters such as cement, such as power plants, refineries, and so on. And then we need to transport it to the CO2 storage site. Then we need to inject it and store it safely and permanently. This is very important. We need to store the CO2 safely and permanently using natural trapping mechanism. So, as you can see here, over the past years, there has been a large acceleration of dedicated geological storage development. Total planned storage capacity has more doubled since January 2022 and reaching over 430 million tons of CO2 per year by 2030. Generally, this provides a positive outlook for CCUS, signaling that strengthened market conditions. This figure shows us that the plant storage capacity is catching up with plant capturing. And that's the good news, that although we are capturing that, now we have some opportunities or plans or potential to already store this CO2 permanently underground. This figure shows us the CO2 emission clusters. As I mentioned, clusters including the steel, cement, chemical, power generation, and refineries, and so on. For example, in North America, as you can see, the red one shows us the clusters and the blue one the sources. We have clusters and sources of CO2 emissions. And we also have the potential of CO2 storage in this area and some plant hubs, as you can see here. Or in the Europe, as you can see, we have lots of plant hubs in the UKCS area and also lots of potential that can be used for CO2 storage. This map shows us the global CCS. These maps provide CCS projects around the world. And here we can find information on large-scale projects, whether they are operating or planned to be operated, which capture, transport, and store at least 500,000 tons of CO2 per year. As you can see, we have lots of projects in North America, in Europe, in Southeast Asia, and in Australia. Some of them are in operation, some of them are pilots, some of them in build, and some of them are in design. This global CCS maps again shows us the different storage types or different underground storage options, which we will discuss about them more detail in next slides. As you can see, in North America, we have saline aquifers or saline formations, which are planned to be used for CO2 storage. We also have some depleted oil and gas reservoirs in Europe, in Australia, and also in Asia. We also have some projects for EOR, CO2 EOR in the Middle East and also in North America and other parts of the world, as you can see from this map. So by this introduction, what is geological storage? Geological storage means that we need to capture the CO2 from industrial processes and then transport it to a storage site. This storage site is an underground geological storage. After transportation, we need to inject it. So we need some injection wells. So we are going to inject those transported CO2 into a deep geological formation, and the CO2 will be in a dense or supercritical fluid that we will talk about this in next slides. After injection and during the injection, monitoring is very important. So we need to monitor the migration of the fluid under buoyancy away from the injection point to see that the CO2 is permanently and safely stored. And finally, the CO2 is permanently trapping by use of different trapping mechanisms such as structural, dissolution, residual, or geomechanical, geochemical, or mineralization. So what are the main geological storage options? The main geological storage options are depleted oil and gas reservoirs. Depleted oil and gas reservoirs are no longer economic for oil and gas production, but we have the infrastructures in place. We have an established trapping system, and we have the storage characteristic that we want. So we can repurpose those depleted oil and gas reservoirs for CO2 storage. The next option is saline aquifer. Saline aquifer refer to any saline water bearing formation. These are not drinking water. These are deep saline aquifer, and mainly their salinity is higher than the sea salinity. The saline formation is sealed by a caprock for permanent storage. So we need a saline aquifer that is sealed by a caprock. Then we can use it for permanent storage of CO2. Another option, these are the main options, is EOR or EGR, enhanced oil recovery or enhanced gas recovery. So which involves injecting CO2 to increase oil and gas production from mature fields. So again, in this slide and in this image, we can see different type of geological storage. As I mentioned to you, the most important one are depleted oil and gas reservoirs, as you can see in number 1. Another option is using CO2 for enhanced oil recovery for EOR. So we are injecting CO2 and then we can enhance and increase our oil production. The third option, as I mentioned, is saline aquifers. We can store CO2 in saline aquifers. The fourth option is using CO2 in deep unminable coal seams. The fifth option is using the CO2 for enhanced from cool bed methane for methane recovery. And the last one, which we have also this option as well, are some basalts, oil shells, and cavities that we can store CO2. But The three mains are depleted oil and gas reservoirs, saline aquifer, and using CO2 for EOR. Here, for any CO2 storage projects, we have 5 main elements. The first one is the capacity. The second one is injectivity. Third one is monitorability. The fourth one, containment. And the fifth and the last one is hydrodynamics. What are these elements? Capacity means that how much CO2 can be stored. And that's very important. So we are going to estimate how much CO2 can be stored in a subsurface, in a geological site, such as depleted oil and gas reservoir or an aquifer. So this is the first element. When we are going to do risk analysis or uncertainty analysis, these elements are very important and we need to consider all of them and then do our risk evaluation. We will talk about risk assessment and uncertainty analysis in the main course by detail. So the first one, as I mentioned, is capacity. The second one is injectivity. When we have the capacity, then we need to inject CO2 for storage. So how fast can the CO2 be injected? This is the second element. The third element is monitorability. So we need some monitorability tools, such as monitoring wells for the seismic and so on. Why? And what are the best practices to monitor and ensure safe CO2 storage during and after injection? As I mentioned, we need to store CO2 safely and permanently. So we need to be sure that this CO2 is not migrating to anywhere else. So we need monitoring. The fourth one is containment. Containment means that what is the risk of CO2 leakage, either vertically or laterally? Is our seal and cap rock sealed? Do we have seal integrity or not? Do we have other, for example, any high permeable zone that can or CO2 can leak from them, or any legacy wells? Do we have any old wells in this area, in this site? When we are injecting CO2, CO2 can migrate to the legacy wells. And if we have leakage in those wells because they are so old, this can be one of our main risks that need to be investigated. And hydrodynamics means that where will the CO2 flow and how will the CO2 plume evolve? So after this introduction, let's have a test together. I will appreciate if you can answer this question in the chat box. So the question is, what is the ideal minimum depth for storing CO2? Option 1 is 200 meter. Option 2 is 500 meter. Option 3 is 800 meter. And option D is 2,500 meters. So please let me know which of these options is correct as the minimum depth for storing CO2. Perfect. Thank you very much. Yes, the answer is 800 meters. Why? Do we know why? We will talk about it in next slide. Why the minimum depth for CO2 storing is at least 800 meters. The next question. What is the ideal temperature for storing CO2? The lower the better, the higher the better. Temperature does not affect CO2 storage. Please answer in the chat box. What do you think? What temperature is better or ideal for storing CO2? Higher or lower, or temperature has no effect? The ideal temperature for storing CO2, the lower, the better. The cooler, the better. Why? Because in cooler, temperature, the dissolution of CO2 into water will be higher. And one of our trapping mechanisms, which we are going to consider it in CO2 storage, is solution of CO2 into water. And that will be happen and will be more in lower temperature. So the answer is A. Test number 3. What is the ideal minimum pressure for storing CO2? A, 200 psi, B, 1100 psi, C, 500 psi, and D, 10,000 psi. Please answer in the chat box. Thank you very much for your answer. The answer is B, or 1100. We will talk about it later, because when we want to inject CO2, the CO2 must be injected at higher pressure than its critical point. We will talk about it in next slides. So, by having this brief quiz, what are the key factors that determine a good CCS site? As I mentioned about the main elements of CO2 storage, the first one is the capacity. So the larger, the better, larger per volume. So porosity of reservoir rock, more than 10%. Net thickness, more than 20 meters. These are the requirements for having a good CO2 storage site. The next element is injectivity. So higher permeability means that higher injectivity. The third element, containment. We need good seal integrity, that CO2 cannot migrate anywhere else from leakage into the caprock or anywhere else. The depths, best depths is between 800 to 250. As I mentioned, above 800, the CO2 will be in supercritical condition, which I will go through that in next slides. And it should be, for a good candidate, to be less than 2,500 meters, because above or more than these depths means that the permeability and porosity will be very low, which is not good criteria for any CO2 site. So in the main course, we will go through the screening matrix, and then we can screen different geological sites. For example, we have 10 aquifers, we have 10 depleted gas reservoirs, 10 oil reservoirs. We want to screen them. Which one is proper or a good CO2 storage site? After that, we will rank them in the main course by examples. And finally, we will select and choose the best CO2 storage site. Temperature, as I mentioned, the cooler the better. Pressure, more than 1,100 psi. And lithology, sandstone are preferred because heterogeneity in sandstone are less than limestones and carbonates. So, another test. Which of the following statement is correct? Desirable caprock are impermeable and react to CO2. Option B. Desirable caprock cover a large area and may be porous, but low permeability prevents CO2 from entering it. C. Limestone are effective caprocks. D. Desirable caprocks cover a large area and have high permeability. Please answer in the chat box. Many thanks. Yes, the answer is option 2. Desirable caprock cover a large area. They can be a bit porous, but they must be low permeable, that prevent CO2 from entering or leaking from that area. So, as I mentioned, desirable parameter for caprocks. The first one, the adequate lithology, is claystone, salt, or halite. So limestone and carbonate are not good lithology for caprocks. Second one, depths. The depths should be higher than 800 meter. Thickness, at least 20 meter, is required to have a proper and adequate sealing rock. So another test and question, what happens to CO2 at depths greater than 800 meter? Option 1, it becomes a gas and occupies more space than it would be at the surface. Option 2, it becomes a supercritical fluid and occupies more space than it would be at the surface. Option 3, it becomes a gas and occupies less space than it would be at surface. And D, it becomes supercritical fluid and occupies less space than it would be at the surface. So please answer in the chat box. Thank you for your answer. The answer is option D. It becomes supercritical and occupies much less space than in the surface. We will talk it in next slide. So what is supercritical CO2? We mentioned that when we want to inject CO2, CO2 must be in supercritical condition. Why? We know that at standard condition, CO2 is gas. When temperature and pressure increased above the critical point, here is the critical point. Critical point, the pressure of critical point is 1071 psi and the temperature is 88 Fahrenheit. Above this point, the CO2 will be in supercritical condition, which displays a property somewhere between a gas and liquid. Supercritical CO2 have a property between a gas and liquid. Its density is similar to liquid, but its viscosity is similar to gas. Then we call it supercritical CO2. CO2 density is a function of pressure and temperature, and it can be calculated based on the pressure and temperature of the reservoir. So what is the density? What is the density change with depths? As you can see, if we considered here a sea level or ground level, when we are going to, for example, 2,500 meters, we can see that the density is increasing. And how about the volume? How about the space? If we consider the volume of CO2 at surface of 100, we can see that in critical depths, which is 800 meters, it will reach to about 0.34. Or in 2,500 meters, it will reach to 0.27. It means that supercritical fluid takes up much less space. It means that we can store more CO2 in subsurface. CO2 has 30 to 40% less density and 5 to 10 times less viscosity than the formation brine. CO2 is lighter than most oils, but denser than gases like methane. So, about CO2 properties, how big is 1 ton of CO2? An adult polar bear weighs approximately 1 ton. A medium car weighs about 1.2 tons. 1 ton of CO2 at surface occupies about 537 cubic meter, 1 ton. But at depths of 800 meter, 1 ton of CO2 will just occupy 1.54 cubic meters. It means that more CO2 can be stored at depths. So we will go through more detail about the properties of CO2 in the main course as well. As I mentioned before, when we are storing CO2, several trapping mechanisms are helping us to store the CO2 permanently there. We can group them into two main trapping mechanisms, physical and chemical, which then can be categorized to structural trapping, residual trapping, solubility trapping, and mineral trapping. We will go through them by detail in the main course, and also we will talk about them, how we can consider them in our dynamic simulation and how much CO2 is going to be dissolved. For example, in the CO2, how much is, for example, free gas and how much is trapped because of residual trapping. We will find them in the main course and in the main simulation project that we will do in next month. So another thing is injectivity and pressure buildup limitation. We cannot inject CO2 by whatever we want. Rate and pressure of the injections are limited. Why? Because when we are injecting, pressure buildup will be happen, and it should not exceed the fracture pressure of the sealing rod. If not, the cap rock will be leak. The safe pressure in case of hydrocarbon fields is initial pressure of the formation. So we cannot go above that. In saline aquifers, if we want to inject, the pressure buildup will be happen, but we need to mitigate that. And one of the way is producing some of the water, because aquifers are different from depleted oil and gas reservoirs. Depleted oil and gas reservoirs have very, very lower pressure than the initial pressure. But aquifers are not depleted, so they have their original pressure. When we are injecting, the pressure is going to build up, and we need to mitigate that. And one of the way is to produce some of the waters to reduce the build-up pressure. So let's have a brief introduction into storage capacity, or if you want to refer to SRMS, storage quantity estimation. How we can estimate the storage capacity? We have two methods. The first one is volumetric, and the second one is dynamic simulation. Volumetric method, we have different formula and equations for aquifers, depleted gas reservoirs, and depleted oil reservoirs. We will go through these equations and formula in the main course by some examples to estimate the capacity of the storage site. Another way, as I mentioned, is dynamic simulation. But dynamic simulation for aquifers, depleted oil reservoirs, and depleted gas reservoirs is different. When we are talking about dynamic simulation, we need to use a commercial software such as Eclipse, T-Navigator, or CMG. But for aquifers, depleted oil reservoir, and depleted gas reservoir, the methodology for dynamic simulation are different. And we will go through in our main course in the aquifer storage and dynamic simulation by a real example and see what will be happened when we are going to implement CO2 storage in an aquifer. And lastly, a brief introduction to dynamic simulation of carbon storage. If we want to use T-Navigator or Eclipse, as I mentioned, for different application, we need to use different methodology or different keywords. For example, we can use CO2 Sol for depleted oil fields. We will use gas vat for depleted gas fields. For aquifers, we need to use CO2 Store, and gas Sol can be used for depleted oil and gas fields. And also, as you can see, for different application, we have different phases. For example, in this one, we have oil, gas, and water. Here we have just gas and water. Here we have gas, water, and solid. solid or salts. And in gas sol, we have oil, gas, and water. So by this introduction, as I mentioned, the main aim of this webinar was an introduction to the main course. The main course is scheduled to be held from 8 to 6 June in the next month, and it is online. And in this course, we will talk about various aspects of underground CO2 storage, as I mentioned, such as estimation of capacity. We will go through by example and see the formula. We will screen, choose the storage site, and also assess the uncertainty and risk involved. So after this course and finishing that, you have these capabilities. First, you understand the component of CCS. Second one, you learn how to screen, rank, and choose the best storage site. You acquire knowledge about storage capacity estimation. You be familiar with uncertainty and risk analysis. And we will practice examples of dynamic simulation of CO2 storage and also about this capacity estimation. The agenda of this course will be, we will cover the introduction, potential CO2 storage, options, depleted oil, and we will go through by detail. In depleted oil and gas reservoirs, aquifers, we will provide some case studies. What are the main elements that we discuss? We will go through them by detail. Trapping mechanism, we just mentioned about the name, but here we will go through them by detail and how they can affect the trapping of CO2 for storage. Then we will go to provide a matrix for screening, ranking, and choosing a storage site, how we can estimate the storage capacity by volumetric and also by dynamic simulation. We will go through by some examples. We will talk about monitoring, verification, and accounting for geologic storage projects. We will talk about uncertainty analysis, risk assessment, case studies, and one example of dynamic simulation of carbon storage using a commercial software. So these are the main agenda of the course that will be held in next month. Thank you very much, Dr. Hassan.
Yes,
back to you.
Great. Thank you very much, Babak, for the nice and very interesting presentation. Before starting Q&A session, I would like to remind you all that Babak teaches the class in this topic in PetroTeach. The course will be offered, as he mentioned, in 8 until 16 of June for 2 weeks in the weekends as online course. And the course includes high-level coverage of technical foundations of CO2 storage and its application in petroleum engineering. Please note that places are limited and will be allocated on a first-come, first-served basis. And for more information, kindly visit our website or send email to register@petro-teach.com. I would also like to mention that this video will be available in PetroTeach YouTube channel, in which you can watch and enjoy. Yes, now we reach to the end of the webinar and hope you enjoyed it. You will receive a link to the recorded webinar and handout notes if you want to share it with your colleagues. Please do not forget to visit our website, subscribe PetroTeach YouTube channel, and download our catalog for the year 2024. Thanks, everyone, and hope you enjoyed this webinar. Thank you. Bye-bye.
Many thanks. Cheers. Bye.